Alright, welcome back to Meteorology 101. Let's get started with some charts this evening. I got the latest data downloaded. I have the base map overlaid onto the radar, the latest radar shot, so we can see where our weather is. We have that low pressure system we had over the north. It was north of Montana. We had to see what's going on with that. We um, got some precipitation, North Dakota, Minnesota, and then we have that low pressure system well to the northeast, and that frontal system that was dropping to the south over the New England states. So looks like most of that's probably snow. We'll have to pull the thickness chart, see where our 540 line is. Maybe I'll pull a radar that indicates what type of precipitation, so we can get an idea what's snow, what's rain. Let's do that real quick, and then we'll start putting some data on this chart and see what's going on. So I'm going to pull the IntelliCast radar. That one shows the rain and the snow. Alright, so looks like the northeast part of North Dakota and northern Minnesota snow. Looks like most of the snow in the northeast is up in Canada. Maybe a little bit of mixture showing up on the radar, but that could just be ground clutter confusing that for mixture also. Just trying to put that line in there. But this band right there through down into Pennsylvania, that could possibly be a front. And then looks like maybe we did have a frontal system extending to the west, so that could be part of this frontal system right here. Went to see what's going on up north, and then we did have a low pressure system to the south over the panhandle of Texas, so I don't see any real major disturbance there. Maybe that model showed that low just kind of wandering around in that area, so I'd say that was just a lee side low that could hang out as high pressure builds over the western states, and then pouring over that ridge, the pressure coming down off the mountains, creating compression and warming to create that lee side low. So let's get back to the charts and pull up some data and see what we're working with. Okay, so right now I'm going to throw some surface plots on here. That way we can see any lower ceilings. We have red, blue, and black. Red is the lowest ceilings. Blue is marginal VFR, 3 to 5,000 feet for the ceilings. And then black is just any ceiling over 3,000 feet. So if you will look at these dots, if they're fully colored in, that's overcast. If they have 3/4 of the colored in, that's broken. Half of it's colored in, like this one, that would be scattered. And then 1/4 of it colored in. We'll see one right away. That would be few, so it's like partly cloudy. So mostly clear, I guess, and then scattered partly cloudy. Broken is mostly cloudy, and overcast is cloudy. So with the red, that indicates IFR conditions. That's for aircraft, instrument flight rules, and the ceiling is between 500 feet, above 500 feet, but below 1,000 feet. Or visibility is 1 to 3 miles. Less than 3 miles, but more than a mile. So marginal VFR is the ceiling is 1 to 3,000 feet, and or visibility is 3 to 5 miles. That's where the blue is. So just looking at these charts, when you see the red, you know you got lower ceilings, lower visibility, and obviously in the precip areas, you're going to have lower visibility. Right there's snow on the eastern part of North Dakota, so snow to the north, east, so your visibility is obviously going to drop. Our ceiling's at 50 feet right there in the northeast. This ceiling right here is 3,500 feet. So maybe even say 3,500 on the 35. So I was looking at, sometimes you could do 300 feet, but that's typically, I don't know if they'll do 350. So with 3,500 feet on that one. You can do a vertical visibility, so you could do ceilings of 50 feet. Like this ceiling's a 4, so it might be 400 feet. And they have like fog and or mist in that area. So visibility's dropped to 4 miles. Visibility's at 3 miles. If you look to the left of these stations, you see number 3, number 4. That's the visibility. Temperature's just above that. Precipitation type. If there is a precipitation, we'll be right next to the station. Then the visibility's out from that, and then the dew points to the bottom left, ceilings to the bottom right, and then your pressure be 1,015.8 millibars, and that's up in the top right corner. So we'll cover stations, all that stuff later, but right now we got the data. Let's throw the surface pressure on here, sea level pressure. Okay, so we're pretty scattered through here, pretty opened up. A lot of calm winds, 5 knots or less. There's maybe a 10, a couple 10s in there. So we're clearing to the south, a little bit of moisture to the north. Maybe need to look at a satellite, see what, probably got clouds. We got an inverted trough here, ridging over the 4 corners, ridging in the southeast. Looks like ridging down through Minnesota. So that low pressure system we had here, if we look at this, we have winds out of the northwest going westerly and then going easterly. So we have the frontal boundary there, or possibly bring this low up into that area, ridging out of Canada, and then as that low tries to move east, it can't because that high pressure is blocking it. So we would have warm air advection in this area. We'll pull some isotherms here in a minute and see where our temperature advection is. And then the ridging to the south, like so, we got the low. That low is pushed way off down into Mexico. We have to look at the data, kind of see if we have any kind of rotation to keep our low pressure system there. I see a pretty good trough right there with that wind shift. So this ridging here is probably a little excessive on this chart. Alright, let's throw the isotherms on and see what we're working with. And then we'll throw the computer generated fronts. Alright, so we get a pretty tight packing here. We got actually a, it's like a cold core system right there. Pretty tight packing all through the north. It's a real strong temperature gradient. So we got a cold air, be a cold front right through here. Probably, since there's no isobars to really give us a pressure gradient, if we brought that front around with this temperature thermal packing here, then we would have to go stationary in this area. Plus with our wind shifts, right here, wind going from the southeast and then from the northwest, that's an indication of a stationary front through that area. I don't see much warm air advection. We do have a 20 knot wind. So if we brought the low pressure, I mean, we got the easterly flow here, westerly flow. We could almost put that low up to the north right there for a little bit of rotation. But we don't have the isobars closed off to really give us our thermal advection. So you're still almost stationary in that area going up into that low. Even right here, that's a low level convergence. A little rotation there, but that's maybe just a little trough. A lot of minor short waves in that area. But let's throw the fronts on. Alright, so it throws highs and lows on there too, so it kind of clutters us up, but I would say it's more accurate maybe to bring that low to the north. They got like a slight bit of warm air advection just because, going low pressure circulating counterclockwise around that low, the way the wind flows around the low, so they're wanting to put warm air advection there, cold air advection behind it. Let's see, I could probably see some cold air advection in that area, so I'd bring, if we had to place our low, I'd actually go south of both of those and then bring that front to the west, for any cold air advection, just the way the wind flows around that low. And then we have two fronts here, so end of trough. So I'm almost looking at, maybe what they're depicting there is like a cold front and then a cool front, or a cool front then a cold front, just trying to separate different air masses based on temperature. These computer generated stuff, so it's like 56, 52, not real huge of a difference there, but 60 to 50, 50 to 44. I mean, we are dropping in that area, so we got, the colder front to the back, but they got a post-frontal trough, a cold front, so I guess a cool front, really, cold front, and then a prefrontal trough. So a lot of troughing going on there. So if we get frontal passage, I mean, we cleared out pretty good today in southwest Ohio. So being between these fronts, we just take that front and then have that cold air behind it, clear that out. If this is even colder, then that's going to clear a lot more out too, unless it picks up any moisture and forces that air up. Then you get your lift. Like, we get cloudiness right behind that front, so that would be like an active cold front. All the weather's behind the front, so creating lift and giving us our lifting condensation level with the clouds. Warm front over to the east, to the northeast, and so that'll be just kind of stable precip. We did see most of the snow was up in Canada, out of Maine, so it's all north of Maine. So we'll have to see where our thickness chart is to judge where precip is. So now we got snow in North Dakota, and then we had rain to the south of that. No stations around here, they're pretty much out of the rain now. This one isn't reporting anything. Calm winds, but the precip, it's just right on the outside edges of the precip right now, so that should start reporting maybe some rain in that area. Alright, so pretty cluttered chart with the fronts. That lee side low, this is actually putting the frontal, when I put the fronts on there, I did put the low back over Texas, and then like a lee side trough just on the lee side of the mountain, so it is still kind of picking that up. The models are handling that pretty decent. The high pressure system, it's kind of ridging in, breaking off, ridging out. It's not really staying consistent on this chart. That models, I think, had that pretty much weakening, kind of sitting in that area. That low pressure system's not going to do anything. So anything in the south, what we're going to get down there is like the wraparound moisture from this high. Any onshore flow, bringing the warm, moist air onshore, and then eastern Texas getting these clouds, and then any type of lift to interfere with that instability, then maybe get some rain showers in that area. So watch for that as you get onshore flow in the Gulf states. Alright, so pretty messy here. We do have that high pressure ridging all the way down into the four corners. Looks like minor short waves around that high. A little bit of cloudiness to the south. 6 miles viz. To the northeast, we still have those systems that were kind of just plowing the northeast. Looks like L3, I'm not sure what that means on that chart. It's maybe like vertical visibility of 300 feet or something like that. We are red, so we are IFR conditions. It's not depicting the visibility. That's this is a buoy, I think, out here anyway. So, or maybe a ship or something. But the northeast overcast, and then winds out of the northwest, onshore flow, just still got the cloudiness over there anyway. So they're getting a lot more rain than they were in a drought. Now they're just getting so much rain that they can't even handle it. So alright, let's jump up a level. Let's get a good look at this low pressure system in the northeast. Even though it's moving out, it's pretty intense. Got some pretty good closed isobars all the way around that low. It's thermal advection to put a double front on here. Let's see, we ought to be able to pick up an upper front from one of those, and then just kind of judge this intensity the same. So let's go to the 850. It's about 5,000 feet. I'm going to let the computer generate this chart just off some scripting, giving it the software some commands. Now, what I should do is erase that radar map, because we're just getting kind of blurred up with the moisture, because I got the script to put the moisture on there too. For anything above 60% humidity, we'll put moisture in the area. So you see where all these black stations are, this cloud cover. So the moisture does match the cloud cover pretty good on this. Sometimes it doesn't. Sometimes you'll get some black stations and then the computer doesn't pick that up and put moisture around them. So let me go ahead and erase this chart real quick, and I'm going to recenter this map. Rebuild our base map. Alright, let's go ahead and run the 850 again. It'll look a little bit better on this map just because it's just simply black and white, or brown and white. So okay, I'm going to do one more thing. I'm going to add some more station plots on the upper levels, because I want to get as many as we can, because there's a lot fewer stations that launch balloons than there are that report observations on the surface. So let me overwrite that. There, we added a few more stations. So pretty tight gradient in the 850, about 5,000 feet. That is a low level jet, 40 knots, 45 knots. We are a low level jet in that area. So having the support for this low pressure system is definitely there. I don't know what this is doing as far as, it's got a pretty deep trough to the north. Let me go put the lows and highs on here. So we do have that low in that area over Quebec. So if we look at a major wind shift, I really don't see one. I see a pretty tight pressure gradient, contour gradient on the 850, and we're not closing off this low. We're well to the north even of that, trying to close an isobar to the north of that, and then maybe even a closed low well to the north. So that's like low pressure troughing, and then trying to bring this as a low. Could be, there's a lot of, not a lot of data in that area, so maybe the computer's just extrapolating that and not getting it right. So, but I still don't see we've got pretty good thermal advection. I don't see a real strong wind shift. So, but the leading edge of this thermal advection, we have a thermal ridge here, a little bit of thermal ridging, and then so we pretty much had an occluded front. If you brought that occlusion around through that ridge and then brought the cold front back, we do have a little bit of wind shift right there. So let me go grab my pen and see if we can draw something out here. And then we'll throw those surface fronts on the 850 just to get an idea. Compare the surface to the 850 and see what we got. Alright, let me get my pen. Okay, so we had to put a cold front on here. I would say, for one, alright, this should be purple, but I'm going to go blue. So bring that occluded front around, maybe through that ridge, and then we could bring our cold front through that trough. We have a dew point depression of 3. Can't tell, that's a 2, 3, 1. So 3 degrees, that would be 0 degree dew point. See, 4, that would be a 2 degree dew point. We brought that cold front around with that thermal advection. I'd bring it right around this area, then actually that would be cold front. So the upper front. Let's throw the surface fronts on here. Okay, now let's bring our drawing back up. Okay, so a little off on that, but our occlusion's pretty close, and then we're shooting that straight down, and then the upper front, I got crossing that front. So if we did what they're doing, we would say our upper front is back behind this cold front. So if that was the case, then we do have an upper front, and that would be a pretty shallow slope on that front. So when you got a high pressure system to the north, all that cold air advection right there, then this bubble up here would actually look like this. So when that front is moving through and the warm air is moving up, then since this is such a shallow slope undercutting that warmer air, then it's pushing that up. So wherever your lifting condensation level is, whatever height that is from the surface to whatever that is, you have to pull a scooty to get your lifting condensation level. You'll push that warm moist air up, and once it hits that level, clouds will form. So let me go ahead and erase this for a second. So when that pushes up, you got your clouds forming. Now if you notice, when you have that shallow of a slope, they're that far apart, then all that weather, there's your frontal boundary. All that weather is at and behind the front. So that's an active cold front. So the difference is between an active and inactive cold front is you'll have, erase that again, if that high pressure system had a steep slope, now your lifting condensation level would be in the same place, but your clouds would form, and this acts more of like a wiper or a snow plow, and then all of the weather stays at and ahead of the front. So that's an inactive cold front. So typically an inactive cold front's a lot faster moving cold front, so steeper slope. You can get the squall lines, just some real quick, tornado touchdowns in, out. The inactive cold fronts, you can just watch your low clouds, mid clouds, high clouds, and then you get into that high pressure system. Then once it gets into the center, your station gets in the center of that high, you just clear out. All the high pressure pushes the moisture out, clears it out. So you can get severe weather from a active cold front too. So don't confuse that for just like fair weather. But you can, as you watch these come through, you have some cirrus overshooting that ridge. You have spillover with cirrus, and you're in this station, you see cirrus coming, you can probably guess, if you're in the right area and the type of system you got, you can see guess what kind of weather's coming next. You'll see the high clouds, all that cirrus blow off over that high. Then you'll start seeing some mid-level clouds. If you're closer to the base of that high, you can see, some, depending on your lifting condensation level, you'll see, lower clouds and then some cirrus, and then you'll start seeing those mid clouds and start seeing overcast start happening. And then as you get basically at, there's your wave, there's your trough, there's your ridge. So at and ahead of this trough would be where your weather is. Anything else pushing down, you'll get that cirrus, you'll get clearing. So you can just get an idea what type of system's coming, or adverse weather in a few days. Just gives you that idea. So, all right, let's go. So that's the low pressure from the fronts that I placed. Let's get rid of that. So we got some troughing in this area on the lee side of the mountains. Cold air advection in that area. We got some thermal ridging to the north, so we got higher heights in that area with that thermal ridging up into Montana, pretty much all the way down into almost to the panhandle of Texas, up through Kansas, Nebraska. There's that thermal ridge. So if you look at a thickness chart, you probably do have your higher heights in this area. Northeast Colorado, stretching all the way up into Wyoming and Montana. So pretty warm. It was like a pretty warm day for that area. Even though this is 12 degrees, 10, 12, 14, cold air advection at 850 millibars. With that thermal ridging is right there on the lee side, pretty much right along the Continental Divide, it looks like, would be the thermal ridging. You'd have a lot of higher heights in that area just because you have downward vertical motion off the mountains, compression, warming way up into the upper levels, or up into the, at least to 5,000 feet according to this chart. So something to think about there. Like if you're reading higher heights on a SCOOT chart in Denver, probably because you have thermal ridging on the lee side of the mountains. You got the compression, you have the warmer air, you will have higher heights. So that would be pretty typical. Probably not for this time of year, but you would see them higher heights just from that compression. All right, so we're veering off here. We're getting a lot of discussion. We're not getting into our charts, which these charts are pretty boring. Got a trough, cold air advection, got that low pressure system. We found the upper front. Still some pretty significant moisture over the Great Lakes region all the way over to North Dakota. And then you have the onshore flow with the atmospheric river pushing those systems right through the northeast. So we still have overcast, still have significant moisture in that area. So let's go up to I think we'll skip the 700 maybe. We're getting a little longer on this video than I wanted to. So let's go 500. Let me get to 500. We'll let this computer run this chart too. Okay, still even at 500 millibars at 18,000 feet, we still have significant moisture in the northeast. We lose it over the Great Lakes region, but over the north central U.S., we still have significant weather up there and some thermal ridging. These isotherms parallel with the contours, so we don't have a whole lot of thermal advection going on. Still got 100 knot winds over the Great Lakes, 75 knot, 80 knot. So we're still cranking some pretty good winds through that area. So that'd be support for these low pressure systems. We got that cold front on the surface. We had kind of that high pressure ridging over Minnesota, so it's kind of blocking that low. So our warm front kind of dropped to the south, and then this cold front came out to the west, and we had that double front on the surface. So pretty good trough, low pressure well to the north. Pretty strong trough. We do get some thermal advection in this area supporting that low pressure system. There's a thermal ridge. We do got thermal advection, so we're still got pretty good support for that system at 18,000 feet. So that system's probably, it's already occluded on the surface with the front, so it's, probably, it's definitely a mature low. So probably getting to its peak and then just keep moving to the northeast until it just dies out, and then this ridge would move into the area and start clearing everything out in the Midwest, Central U.S. The ridging over Texas, this is at 18,000 feet, so 500 millibars. So we do got ridging in the upper levels. That is just another indication for this area to have, higher heights. Like I said, if you get a reading on a SCU-T chart for 500 millibar, you can go, 5,000 meters. Just to see what your heights are, that indicates, warmer air, higher heights. So you'll get those readings, all through, pretty much through that continental divide. I mean, we're seeing a little bit of ridging through there still. So, all right, the 500 millibar, we're going to go ahead and pull that 500 millibar vorticity advection. Now we'll see where our positive vorticity advection is, and then that will indicate areas of upper level divergence and instability. Let me get my pen on this one. We'll see what we're working with. So we see the contours. I don't see a whole lot of advection going on there, but let me try to turn this off a second and bring that up. Okay. Clear that out. We do have positive vorticity here. Really not a lot of advection though. We do got some right in that area. That's crossing a little bit, so it's pretty close in that area for that positive vorticity advection. A little bit of crossing here, so that's indicating pretty good. And then that strong advection, definitely see that strong advection in the northeast. That's closed off. So yeah, we got pretty good advection up there. So that system's just cranking. This one here looks like it could be developing. Continues to develop. We had that high pressure kind of ridging in on the surface. It's not coming up very high. And then little bit showing positive vorticity advection in that area. I don't really see it a whole lot, but upper level divergence right there, lee side of the mountains, that all makes sense with that thermal ridging that we had. That was all the way around up to into Montana. So that's all making pretty good sense there. Now if we get a low pressure system like this one, this indication of positive vorticity advection is going to give us an idea if that low pressure system is going to intensify, the frontal system is going to continue to undergo frontogenesis, strengthen, then, that gives us the indication of that. So I do have a chart that we can pull for frontogenesis. Let's go pull that real quick. Gotta get this back to center. And let me go back to the surface. Run these scripts. I'm going to run them at the level they're supposed to be so I get the right data. Okay, it didn't erase that chart. So there. Okay, I got it. There's our frontal systems, low and highs. Let's go with put some pressure on here. The sea level pressure. We already got our front, so we said, this low is pretty accurate, I think, in this area. We had that trough, we had that kind of stationary front coming up into that, so it's showing an area that could develop. And then that low to the north, where we've seen that disturbance, that warm air advection over North Dakota, some a weak chance of that developing. There's the high pressure system that's ridging down out of Canada into Minnesota, so it's kind of blocking this low, and then it's got that warm air advection, drop it to the south, and because it's just cramming up against that high. The low can't move the high, so it just smashes that warm air up against the high, so you'll get lift, and you'll get the adverse weather because of that low pressure pushing into that high and causing your lift. So this front coming out, we still are under pretty good frontogenesis. If you notice, this is pretty much goes in hand with the positive vorticity advection. So we have upper level divergence. That's an indication any thermal advection, that frontal system is going to intensify. So we had this well-developed low to the northeast with that frontal system. That's going to continue to develop and then just move out to the northeast. And then we'll have to see what happens with this front. If it stalls out, becomes stationary, because these isobars behind that are so far apart, that front would almost just have to stall unless this high pressure just pushes down. Now we have that cold air advection and starts intensifying that cold front again. Gives it, the leading edge of that air mass. That's what a front is. It's the separation between air masses. So this drops down, gives us that cold front, and then pushes through. And then we have lift, any moisture, instability, Indiana, Ohio, then we can get, some rain showers out of that. If there's the moisture availability. The instability to cause that, that's pretty much what you're going to have to look for. The upper level divergence, so you can get a dry high pressure system push through. You don't have the moisture instability, so it just pushes a stable environment up, and it wants to go up. So we're a stable environment wants to stay the same, but you're pushing a air partial where it wants to be. You push it, push an air partial up, and it's basically have to be neutral and just stays there. There's nothing. It doesn't want to come back down. Doesn't want to go up higher. It just stays where the air mass pushes it to. So you got to have the instability and the moisture for the high pressure to move through and cause adverse weather. All right, like I said, we veered way off on this thing. So let's get back. Let me get back up to the upper levels. Let's go 300. We'll pull the jet stream. Alright, this is pretty intense. We got a strong jet stream up here. Okay. Let's go put our contours on. Isotherms. And then station plots. See what kind of winds we have up here. 150 knot winds. Okay. 190. That's 140. 135. 150 it looks like. So it looks like a max of 150 up here. But man, that's pretty strong. Jet max. This chart's kind of just extrapolating this, just shooting it straight out. It doesn't know what to do with that. There's no data there for it to use, so it's just kind of taking that jet max and shooting it straight out over the ocean. But either way, this is still accurate data. We have pretty high intensity winds over the Great Lakes region. We got that low pressure system to the north. Trying to figure out with that low to the north, occluded front. It had to be an occluded front dropping down pretty far, and then the cold front coming to the west into that stationary front or that low that we've seen over like South Dakota area. Because you can't have a jet shooting straight across the front. It's going to kind of follow that front. And then if it crosses a front, it's going to cross right at the triple point, right at the beginning of that occlusion. So it's going to cross that occluded air, not the cold front or the warm front. It's going to kind of ride with the cold front and the warm front. So either way, pretty intense jet stream. Upper level support for the low. We said that low was undergoing frontogenesis with those fronts, so we were, saying, it could intensify. This thing, if you have this jet max moving in to this trough, then that trough should deepen. It will cause that low pressure system to become more intense. It will build that, strengthen those fronts and give it that support that it needs. So, alright, this video is going on long enough. I am going to call it quits. We will hit the 300. Hope you learned some techniques on this stuff. We did veer off and went a little sideways, but it's all it's improv. We don't script anything. I just get out here do this. So if you like what you heard, like my video, give me a thumbs up. Until next time, get your head in the clouds.